Hello, students. So, remember when we were proving some of the identities involving n choose k, and I said that there was one with many messy denominators that we wouldn't want to combine? I want to take another look at that. So, what I was asking was for a solution to this. N choose 0 plus n choose 1 plus dot, 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 all the way over to n choose n. And of course, we found a way of figuring out what this was very simply by thinking about these as actual physical choosings of things from subsets. But now that we have the binomial theorem, we have another way of going about it. So just one more time, so we have it on your screen. This is going to be n choose I, x to the I times y to the n minus I. So if I'm thinking about this, what could I do if I just wanted the binomial coefficients from 1 to n? Well, keep in mind that this is a statement that's true for any numbers x and y. So what numbers would I want x and y to be? I could set x and y to both be 1. Oh, and keep in mind what we have to write down what this is equal to. This is equal to x plus y to the n. Okay, so what happens if x and y are both 1? Well, if x and y are both 1, so this is true. So therefore, it must be true for the case where x and y are 1, which would give me just an n choose I on the left, and on the right I get 1 plus 1 to the n, which is equal to 2 to the n. So that's another way of showing this identity, which is nice and easily done. And of course, there's all sorts of things that you can do in order to sort of manipulate this. For example, if you just wanted to plug in 1 for y, you get another identity. I equals 0 to n, and choose I, x to the I. So suppose we just wanted to sum this. What would I get? Well, this is the sum of x plus 1 to the n. And, I mean, this is a bunch of terms. This is a polynomial in x. This is an expression. If I wanted to, I could do things like differentiate both sides, and that's perfectly fine. If I did differentiate both sides here with respect to x, what do I get? Well, I get n choose I times I x to the I minus 1 is equal to, okay, well, I used a chain rule here, n x plus 1 to the n minus 1. And of course, this is times the derivative of x plus 1, which is just x. Okay, but keep in mind in the I equals 0 case, right? So in the I equals 0 case, this was just a constant. It should have gone to 0. It really doesn't matter because I have a 0 here for I, but I could start this with 1, and it doesn't make any difference. And then you don't have to worry about the negative exponent there, whatever. But in any case, I get this identity, and this can be used to prove all sorts of things as well. For example, I don't know, let's say if x is equal to negative 1, yeah, that's sort of famous. So what we get here is the I equals 1 to n, and choose I times minus 1 to the I minus 1. So how would this start? This would start with the I equals 1. This would be 1 minus 1, which would be 0. So this would be a positive I to the n, choose I. Or I should say 1, and choose 1. And then this goes up to 2. With a minus sign, and choose 2 plus 3, and choose 3, and then so on and so forth until we get all the way up to n. And then what is this equal to? Well, the right-hand side is just 0 because minus 1 and 1 give me 0. So that is yet another identity that we can prove using the binomial theorem. So lots and lots of different identities that we have here. Maybe I want to talk about this. What would happen if we just wrote out what these binomial coefficients were? So I'm just going to write this. 1, 3, 2, 3, 3, and so on. And what are these? Well, these are the different coefficients. These are the coefficients of x plus y to the 0. These are the coefficients of x plus y to the 1. 1 and 1, of course. These are the coefficients of x plus y squared, x plus y cubed, and so on. So if I were to keep going, I'd get the coefficients of x plus y to the n for any n. Okay, and what are they? Well, this is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And if we were to keep going, I would get things like that as well. And this is famously known as Pascal's triangle. Because of a paper that was published after Pascal died, it wasn't known as such when Pascal was alive. And Pascal was over 1,000 years too late, because this was known to mathematicians in many other places, including China. And in India, he was beaten like really a long time ago. Virahanka studied this, but this is not history of math. Just know Pascal wasn't the first guy to do this. This was known and rediscovered separately many times for certain reasons, many of which involved music and rhythm. But sticking to this. Okay, so what were we going to do here? Well, if you've known Pascal's triangle, the inappropriately named Pascal's triangle, then you probably know that each of these numbers is going to be the sum of the two above it. You'll notice 4 is 3 plus 1, 6 is 3 plus 3, and so on. So what must that mean for the binomial coefficients? It must mean we have some sort of an identity, which we do. If I were to take any binomial coefficient and choose k, what would the coefficients be above it? Well, you know what? No, I want to take a situation like this. Yeah, I think that's a little. If I take any two binomial coefficients who are next to each other in this pyramid that I've set up, I know that the one that would be right below it and between them would be the binomial coefficient n plus 1, k plus 1, if this is n choose k and this is n choose k plus 1. So what this means is if Pascal's identity works for these binomial coefficients, I mean, maybe this property of each number being the sum of the ones above it doesn't work. It does, but we don't know that for sure. So why don't we prove it? Or why don't you prove it? How would we prove it? Well, if we could show that this plus this equals this in terms of binomial coefficients all of the time, then we would have a proof. And there's two ways to prove it. I'm going to leave that for you to do because it's kind of fun. One thing you can do is you can just do it algebraically, write things out in terms of the factorials. That's not as interesting. But think about what this counts on the right, n plus 1 choose k plus 1. And think of a way that you can interpret ways of choosing something from a collection of n plus 1 objects as choices involving a collection of n objects. And if you could think about that, remember you have your rules from counting, rules of counting already. I think you can find another more elegant proof of this fact. And then once you've proven this, you know that you can just take the sum of the two above it, and you'll always get all of the binomial coefficients in that fashion. So that's some stuff that can be done playing around with the binomial theorem.